So in the previous lectures, we have learned much about the basics of the STAAD software and what are the various different options to do various automated functions that are available with the help of STAAD software. Now we will move on to the practical case study. So in this practical case study, we will design a simple school building, and in this school building we will learn about the Indian standards and what exactly our Indian standard guides us, that what kind of loading we should take, what are the seismic coefficients, what are the seismic parameters, and how we can do the design, and in the end how we can detail the structures also. So this is basically a simple perspective view of how we can what kind of school structure or what kind of school building we are making here. This is called for every project there's also a project development site also. So here we can see that this is basically the site which is opposite to the church, and these are the roads that are being shown here, and there is also a vicinity map for every project. So this we can say that this is a national road, and on the left and this is this site, and on this site we need to make this school. So first of all we start with the first floor plan. So in total we have first, second, third, fourth floor plan and roof deck plan. And if we want to see the elevation or the front side view that we were seeing in the 3D perspective view also. So here this is the first floor finished floor level, which is 0.6 meter above the natural NGL level. It is also called the natural grade line or natural ground level also. So between first floor level and second floor level, the difference in height is 3.5 meter, then again 3.5, 3.5, and then in the last it is 3.2 meters. So our building is basically having, this is the first floor level, second floor level, third, fourth, and roof deck level. This is the left side view here, and this is the rear side view, that is the view which shall be seen from the back side, and this is the right side view. So coming back to the plans here, so first of all, if we want to see the first floor finished floor level, which is at 0.6 meters here, so here we can see that this is the simple first floor plan. So we have 1, 2, 3 and 4 classrooms, 1 office, utility room, and this is one big corridor here, and corridor width is approximately 2.5 meters, and this is a washroom here, and this we can say this is a storeroom. So this is a staircase for access to the upper floors. So the flight is starting from here. So that is why this is marked as hidden, because if we are standing here, we won't see the full flight from this point to this point. So this is the like a mini hospital that is required in every school building. And here we can see that there are like small steps here, that is 1, 2, 3 and 4. And similarly there are 4 steps here also. Some of you must be thinking why we have provided these steps on the this first floor level. The reason for that is because the first floor level is at approximately 0.6 meter from the natural grade line level. So 4 into 150 mm. Usually the riser of the staircase is 150 mm. So 4 into 150 is basically 600 mm. So that is why we need 4 risers to have an access to this building here. On the right you can see there is also a ramp also. So ramp is also a statutory requirement for buildings, and here also we can see that in addition to the staircases here, we have a second way to go to the top. So that is why we have a ramp here also. So this is just a simple school building. On the left it is hospital for first floor plan, on the right there are offices and utilities, and here there is the ramp. So if we want to see the second floor plan also, so all the rooms are classrooms here. So we have 1, 2, 3, 4, 5 and 6 classrooms here. This is the washroom. So this must be for the men and this must be for the women. We will see a separate drawing for this washroom area, but for understanding, second floor plan is just simple, and the third floor plan is again simple, almost similar to the second floor plan. That is, we have 1, 2, 3, 4, 5 and 6 classrooms, ramps, staircases and washrooms. Again fourth floor plan is also same. After that, a simple roof deck plan. So on the roof there must be a parapet, and after that we have seen the front side view here. So we just need to understand the levels here and remember them, 3.5 and 3.2 here. So in addition to that, this is a drawing for the ramp. So here we can see that this is just a simple ramp detail here, and to access to the ramps we have this from first floor to the second floor. So we do need 2 flights here. So this is just a simple way to show the ramp sections, and this is just a simple staircase detail. So we do need approximately 20 steps to reach to the top. So if we want to see the levels here, so we do need to climb 3.5 meters here, and to climb 3.5 meters we can take the riser of 175 mm. So 20 into 175 mm, so it is 3.5 meters. So that is the simple math that architect has done here. So after that we can check the washroom layout plans also. So on the first floor, this is the storeroom that I had discussed with you earlier also. That is for this is the gents washroom and this is a women's washroom here. After that you can access the second floor, third floor and fourth floor plan also. So in this lecture we shall learn about the much widely asked questions, that how we can convert the architectural drawings into structural drawings, and what are the major things that we do need to keep in mind while we are planning the structures. So starting from this first floor plan, we have different rooms here. So first of all, first approach should be that your column should not be hindering the architecture, or I should say that your column should not come inside any rooms and it should not come inside any corridor. So starting from this room here, or we can first of all start from easy point here. So overall, if we see the spacing between the size, if you see the size of the classroom, it is approximately in the range of 9 meters here. So we we cannot say that we can go from this point to this point in without any column, because in that case for 9 meter span the size of the column shall be and the size of the beam shall also be very large, and it shall make your building ugly only. So instead of that, what we can do here is that we can provide column spacing in the range of 4.5 meters. So the advantage of this is that your size of the beam shall be reduced and you shall have more number of columns. So in this case, to plan the structure for, let us say, this classroom, I have taken 1, 2, 3, 4, 5, 6, 7 and 8 columns here. So here also in this, along this span, the size of the room is very high, that is in the range of 7 meters. So if our tendency shall be that we shall provide a column here also. So along this direction we are providing columns, we can provide columns in the spacing of 4.5 meters, and along this axis we can provide columns in the spacing of 3.5 meters. See, lesser the span of the column and the span of the beam, the less load shall come on that, and more economical your building shall be. So here we have targeted the alternative approach, as I had discussed with you earlier also, that our column should not come inside any room or inside any corridor. So we are not providing any column here. So that is why the spacing of this is in the range of 7 meters. So if we are providing beam from this point to this point, this beam shall be lightly reinforced and smaller in size, but this beam needs to be somewhat larger in size, and reinforcement shall be higher on both on the positive ends as well as on the negative ends. So this was just a simple arrangement here, that is one column here, we can hatch this column here. So one column we are providing here, other here, after like spacing of 4.5 meter, then again here, then again here. So now we have provided columns at the spacing of 4.5 meters. Now this whole area is done. After that, we do need to shift our focus to like grid number E here. So on grid number E, we have provided columns along the walls only. So we can provide a hatch pattern here also for our clarity. So we are providing these columns at the spacing of 7 meters. So as it was possible to provide column here, so that is why we have provided column here, but we are not providing any columns here. After that, we shall study about how to provide structure for the corridor area. So in corridor area also, we can provide the same type of arrangement, but in the spacing of 4.5 meters. So that is why we can provide columns here and then after that here. As there is no harm in providing column, like providing column here. So to avoid the span of 9 meters, we can provide columns at the spacing of 4.5 meters. So it's not like we cannot design the structure for 9 meter span, but the thing is, as a structural engineer, you should like target for the maximum optimization. Maximum optimization in terms of economy, money, costing, and lesser beam and column sizes. And so we have planned the one side of corridor here, and then after that again here also we can plan the corridor. But like for the structural symmetry of the building, whatever columns we are providing here, so that mirror image we will provide column here. Plus this is the front end of the building, so as for the architectural aesthetical purposes also, this column will look good here. So it is not like columns are always ugly, but they do add to the architectural element sometimes, or they can make the building look beautiful also. Structural planning is a very like important job of a structural engineer. A good structural engineer shall always do a good structural planning, and vice versa also. I do seen various like structural arrangements that seem deemed to be like designed by some but novice engineers also. So do make some permutation and combinations of the different types of arrangement, and then target for the maximum economy also. So now we have planned this whole corridor area here, and then after that we can provide columns here also. So this is basically the staircase here. So we shall provide a mid landing beam here, not floor beam here. So that thing we do need to take care while we are modeling the structure. We do need to think about this ramp area also. So in the ramp area, we are having upslope from this point here. So we what we can do here is that we can provide cantilever beams from this column here. So by providing cantilever beams, the span of this beam is approximately in the range of 1.8 meters only. So for 1.8 meters, 230 by 450, or I can say 9 inches by 18 inches beam is more than enough. Or to control the vibrations, what we can do is that we can provide a thicker beam also. So 12 inches by 18 inches beam is more than enough for this particular ramp here. But in modeling, it shall be very difficult for us to model the whole ramp from this point to this point. So what we can do is that we can stimulate the whole area by providing a simple floor on the top, and that thing we will discuss in the model. But when we are doing the structural designing, we do need to do some approximations also. That is to convert from physical to analytical model. There are always some approximations. So now we have planned the columns for all the locations here. So now I have made all the columns in yellow color and have changed the layer of these columns, and I have also made a block of these columns. The reason why I have made a block of these columns because I want to superimpose this particular column layout plan on all the floor levels. So this is the approach that we should always follow when we are doing the structural planning, that whatever the columns we are finalizing on one columns are feasible on the other floors also or not. So I have just copied paste the block on the second floor plan. So here also we can see that the columns are not hindering anywhere, or they are not coming inside the classroom, and they are not coming in the corridor also. So similarly we do the same for the remaining floor plans also, that is for third and fourth floor plan. So here also we can see that all the columns are correct, but this column is not correct here, and this column is also coming in the classroom here. So we cannot take this particular column here. So we do need to remove this column from this point here. So what we can do here is that we can change the block here. So 1 2 3 1 2 3 1 2 3 1 2 3. So we do need to delete this particular column here. So there shall be no column here, and the same shall be applied here also. So that was the advantage of making a block and superimposing on all the floors, so that we can find what exactly is the situation. Although we can provide the column here, but that column needs to be terminated on the upper floors. So to make the thing simple, what we can do is that we can follow the same system. So here also the columns are now correct, and then we can copy that on the fourth floor plan also. So here also the columns planning is correct, and on the terrace we don't need to superimpose that, because in that floor plan the columns will automatically get terminated here on this floor plan. So now we have planned the column locations. We can tentatively like plan the column sizes also, so it all depends upon the experience. So although there are thumb rules, but those thumb rules are also somewhat typical to like apply in the real life. So for this location here, I have provided 350 by 600 columns, and if required, we can increase the size of this particular column to 400 by 600 or 400 by 750 mm. So similarly for the small square columns, right now I have provided 350 mm, but that I think do need to increase to 450 by 450 mm. That we can see when we are done with the structural designing. So here also we have provided 350 by 600 columns. The command to check the dimension is nothing but DLI. So here we can see a dimension linear, and press the space bar again so that it can automatically dimension. Or if you want to do the dimension manually, what we can do here is that we do need to click once here and then click once here. So here also it is 350 by 350 mm. And for ramp columns also, tentatively right now we can take 350 by 350 mm, but that do needs to be increased after analysis. So for this beam, we can also do the beam planning in the later stages, but right now in this lecture we are done with the planning of the columns. So in the next lecture we will start with the STAAD software, and then we shall do the basic framing of the whole arrangement that we have planned here. So in the previous lecture we have learned how we can do the basic column planning. So in this lecture we shall try to convert this physical model into an analytical model. So first of all, starting with the editor file, we can have the units as meter and kilonewton, and have our first joint coordinates at the location of origin only. So pressing Shift plus K option on my keyboard, and the first grid is at 4.5 meter. So I can take 4.5 meter here, and the second is also at 4.5 meter. And these two joints shall be translationally repeated at 3.5 meter spacing. So I select Z as 3.5 meters, and then this whole arrangement shall be repeated at Z equal to 7 meters. So now we have drawn this particular arrangement here. And to make the thing simple, what we can do is that we can model a basic beam arrangement here also. You should note that we are making the model at the first floor level. That is for this first floor plan, which is at 0.65 meter from the natural grade line or natural ground level. So the next arrangement is that just the copy of this. So what we can do to save our time is that we can press Ctrl C, Ctrl V option on my keyboard and select X as 9 meters. So now this arrangement is repeated, and after that we do need to repeat the same arrangement by 1, 2, 3 and 4 times. So we select this arrangement, press translational repeat, select default step spacing as 9 and number of steps as 4, global direction is X. So now we have starting from the office area or hospital area, sorry. So starting from this area, this is the hospital area here, and after that we do need to have 1, 2, 3 and 4 classrooms. So 1, 2, 3 and 4, and after that this area shall be the office area and utility room. So now we have drawn this arrangement, but there is this one thing that we should see here, that there is this 0.5 meter gap here. So what we can do in this case is that basically the spacing is from this point to this point is now 9 meter again, but actually the we don't need to worry about this, because this column location is at 4 meter from here. But this arrangement is typical, so this is correct. And after that we do need to model the corridor area also. But before that, what we can do in this area is that we can draw beams here also. So, and again, to make the arrangement simpler, what we can do is that we can model beam in this direction also. So to make the thing simple, what we can do is that we can go to geometry, add beam by perpendicular intersection. And again go to add beam option here. So now we have drawn full beam arrangement here. And after that, what we can do is that we can model the corridor area also here. So going to the corridor area, what we can do is that we can see the spacing here. The spacing is 2.5 meters here. So we do need to select this whole area here. And all of the columns are being translationally repeated except this particular column, so that we can take care in the later section. But to proceed further, we can press translationally repeat at 2.5 meter spacing. And after that, similarly we can draw this area also. So we do need to have a 1, 2 and 3 and 4. But to make the thing simple, I will request you to undo it. Please don't add beam at this point. The reason I will tell you in the later stage. But just model the column first. So these are the columns that we do need in our structure. And after that, just select this arrangement here and translationally repeat along Z as 2.5 meters. So number 1, 2, 3 and 4th. So first, second, third and fourth. So this particular column needs to be shifted by 0.5 meter on the left. So what we can do is that we can delete the beam here and select this node and go to geometry, move, joint and select X as minus 0.5. Select retain connections here. So now we have shifted the joint along X direction. And after that, these particular 4 columns do need to be translationally repeated at the spacing of 4.3 meter. That is 2 meter here and 2.3 meter here. So selecting these particular columns here and selecting axis as Z, default step spacing 4.3 meter and link steps. So now we have all the joints at the column locations only. And after that, there are no columns here. And on this area, we do need to model the ramp area also. So what we can do is that we can select the joints here, and we do need to copy paste at 4 meter spacing. So selecting Ctrl C, Ctrl V option on my keyboard, select X as 4, and we do need to 2 columns here also. Add the spacing of 2.2 meters. So selecting Z as minus 2.2. And selecting this joint also, add the spacing of 4 meters. Similarly for these 2 points also. And this grid spacing is 2 meters. So we do need 2 columns at Z equal to 2 meters. So now we have modeled the ramp area also. So this is the simple geometry of the structure that we are making. So now basically we have modeled the columns. Model the columns in the sense that wherever there are columns, we have a joint there. So what we can do in this case is that, like in this elevation, the first floor plan is at 0.6 meters. So let us say if we want our foundation at 1.5 meter below the natural grade line, that is NGL. So the height of the column shall be 0.6 plus 1.5, that is 2.1 meter below the like first floor level to the foundation level. So selecting translation repeat, so selecting global direction as Y and default step spacing in -2.1, and selecting link steps, we can see that we have now modeled all the columns here. So this was just a simple exercise to like model the first floor level. So now you can easily understand what exactly was the purpose of selecting like only columns here, so that we can easily translationally repeat all the joints in the -y direction with the spacing as required. So now we do need to model this second floor plan. So now there are two approaches as done by the like most of the people. One approach is that they just model the whole structure and then after that they assign the properties. Second approach, or like smart approach that we can take, is that we can assign the properties here, and then we can just simply translationally repeat them to save our time. But following the first approach only, because I don't want you to get confused. So what we can do is that we can make the whole model first and then we can later on assign the properties. So coming back to our model, now we can easily check that whether the modeling we have done is correct or not. So as far as I can see, the modeling is correct. So now this whole arrangement, that is at the first floor level, this whole arrangement needs to be at the 3.5 meter level also. So coming back to our model here, so what we can do here is that either we can model the beams along this direction also. The reason for modeling beams along this direction is that we do need to break the slenderness or the axis of the column along this direction here. So I shall already advise you to make this beam here. And we can make the beams here also. See, a good structural engineer will always tie the columns as much as possible, because he know that as much as we tie the structure will be more economical and integrated in the at the time of the earthquake. So what we can do right now is that we can translationally repeat the whole structure. Selecting global direction Y and default step spacing, as we know that the height is in the range of 3.5 meters. So select default step spacing as 3.5 meters and select option of link steps. But we do need to delete the stub column that we have modeled here. So here you can see that there is one small stub column. So delete this particular column here, and now we are done. So on the plinth level, if we want to see the structural arrangement again, now the arrangement is okay, but the thing is that this column is not getting tied in this direction here. So what we can do is that we can provide alternate ties. So we can go to add beam by perpendicular intersection. So we can provide alternate beams here. As on the plinth level there shall not be any structural slab, but by making this beam, what we are doing is that we are breaking the length of this column along this axis so that the reinforcement shall be less, and all these beams shall need to be released at the end point. So we go to specifications and we go to beam, start, end, my and mz. So now we have released the beams on the on this point. By releasing, what we mean is that at this point there shall not be any moment transfer capacity, only shear force shall be transferred from this beam to this beam. So for this beam also the case shall be same. So now we have made a fully satisfying model at the first floor level. After that, if we go to the second floor level, we do need to provide the beams here also. The reason for that is because our span is approximately in the range of 4.5 to 7 meters. We shall make the slab very heavy. So to break the span and to tie the columns along this direction also, so we go to geometry, add beam by perpendicular intersection. So by making all the beams here, we can just tie our structure. So now we can see that in the plan view, the spans of the slab are less. That is in the range of 3.5 to 4.5 meters, which is not a very big deal for slab design. And for ramp, as I had discussed with you earlier also, that I shall not be modeling the ramp here, but to make sure that the ramp loading is being considered, what we can do is that we can provide a full floor slab here, and then we can apply the loads so that the columns and the foundation shall be designed accordingly. But if you want to do the fine-tuning exercise, or if you have sufficient amount of time, then what we can do is that you can provide a cantilever beams on all the columns along the ramp profile. But as that was a time-consuming approach, so to make the thing simple, I am following this approach. So coming back to our model here, so now we have modeled the second floor plan also. After that, we do need to model the this third floor level. Now we are standing at this particular level, second floor level. So after that, we have third floor level also and fourth floor level also. But third and fourth are just a copy of second floor plan. So in this case, what we can do is that we can just translationally repeat this whole structure along Y. Default step spacing is 3.5 meter and number of steps is 2. So now we are standing here. That is first floor level here, second floor level here, third floor level here, and fourth floor level here. After that, we do need to repeat the arrangement on the spacing of 3.2 meters. So in this particular case, what we can do to make the thing simple is that just translationally repeat this whole structure along Y. Select default step spacing as 3.5 meters, link steps. Select all the beams here, go to geometry. Geometry, move, joint, select Y as minus 0.3 and left click on retain connections here. And now we can see that this is 3.2 meters. So this was just an approach to save the time, and that we have already saved with the help of this approach. But overall the modeling has been done, and in the next lecture we shall learn on how to give the properties and how to assign the floor loadings. But before that, I shall teach you about the basics of the Indian standards loadings. That is, what are the codal guidelines on the loadings that needs to be applied on the school buildings. So in this lecture, we shall first of all have a basic introduction of what our code guides us about the various type of loadings that shall act on the structure. So in this lecture, I shall only introduce you about the live loading that do acts on the school building, and what are the values as per the Indian standards for various type of rooms in a school building. So accordingly, either you can refer to NBC 2016, that is National Building Code, or you can refer IS875 Part 2. So Part 2 has the is the code for this live loading that shall act on a structure. So in post loading, or either we sometimes say it as live loading. So for the code has adopted a basic terminology. So the code has divided the various type of structures into either they shall be named as assembly buildings. So under that, theaters, motion picture houses, city halls, marriage halls, etc. shall come. Business buildings. So business buildings are nothing but the like offices, banks, courthouses, libraries, etc. Either they shall be dwellings. So either they are also called as apartment houses. Either educational buildings. So like our structure comes under this terminology, that is 3.2.14.4, that is educational buildings, or they are also called as industrial buildings, or we can term it as institutional buildings. So institutional buildings are nothing but like medical buildings, or for persons suffering from physical or mental illness, or hospitals, penal institutions, jail, prison, or reformatories. So coming back to our code, so it is also adopted in into office buildings, mercantile buildings. Office buildings are nothing but the buildings that shall be used for work, handling money, telephone, telegraph, operating machines, etc. Mercantile buildings, residential buildings, or storage buildings. Storage buildings are nothing but warehouses, cold storage, or storehouses, garages, etc. So coming back to our this table 1. So table 1, first of all, it is guiding us about the residential buildings, dwelling units, hotels, hostels, and second is the education buildings. So under education buildings, there are two columns here. So the number one column guides us about the uniformly distributed load, that is, it directly gives us the flow load in kilonewton per meter square, or it gives us the concentrated load in kilonewton. So the code guides us that whichever is detrimental for the structure, you shall use that. But usually as a practice, we do apply this flow loading only. So for classrooms, the loading is 3 kilonewton per meter square. For canteens or restaurants, it is again 300 kg or 3 kilonewton per meter square. For offices, lounge, and staff rooms, it is 2.5 kilonewton per meter square. For dormitories, 2 kilonewton per meter square. For kitchens, again 3. For washrooms, it is 2, and for storerooms, it is 5. And for libraries, it is minimum of 6 kilonewton per meter square, and up to minimum height of 2.2 meters. And if your library height is beyond 2.2 meters, then for every meter beyond 2.2 meter, you shall add 2 kilonewton per meter square. So for example, if the height of the building is 4.2 meters, then it shall be 6 plus 2 plus 2. So the total loading shall be 10 kilonewton per meter square for height of 4.2 meters. And again, it is also guiding us about the boiler rooms, corridors, passages. Again, it shall be 4 kilonewton per meter square, and for balconies also, it shall be 4 kilonewton per meter square. So coming back to our model here. So in our model or in our structure, we have on first floor plan, we shall not apply any loading cause it shall rest on the ground only, and but except in this area, we shall only apply the brick wall loading here. So in this lecture, we shall only learn about the loadings that shall be acting on our structure. So here there are various classrooms here. So in all the classrooms, we shall apply loading of 3 kilonewton per meter square as guided here. And after that, same shall be applied here also. And for corridor, that is in along this area, we shall apply loading of 4 kilonewton per meter square as it is guided here. And for washrooms, we shall apply loading of 2 kN per meter square. So in this area where there are two washrooms, we shall apply loading of 2 kN per meter square live load. So now you must be having clarity here that how and what are the superimposed loading or live loading that needs to be applied on the structure. And this area that you know, like some people must be wondering that why we are not applying loading here, because it is just a simple fundamental concept that on this area, that is on first floor level, this whole area is resting on the ground only. So whatever loading that is being coming here, it shall be transmitted directly to the ground. So except for the brick wall, we shall not apply any loading here. So in the next lecture, we shall assign the properties of the beams and assign the properties of the columns. So in this lecture, we shall learn how to assign the properties of the columns and beams to the various beams and columns that we have modeled in the STAAD. But before that, if we access the structure, then we have tentatively given the sizes of 350 by 600 mm on all the columns along grid F. So coming back to our model, before assigning the properties of the columns on the grid F, we do need to do a simple correction here. Here you can see that there are various stub columns that have been produced as the result of translational repeat. So what we can do as a simple step is that we can select this whole grid here, go to view selected objects only, and then select view from +Z. So deleting all these stub columns here. Now we are fine with the model. So coming back to these columns here. So all these columns are of size 350 by 600 mm. So we go to general property, go to define and rectangle, select Z as 600 and Y as 0.35. Left click on add here, go to select beams parallel to Y axis and go to assign to selected beams. And if we select this beam and go to isometric view, here we can see that the orientation of these columns are correct. So similarly, we do need to follow the same approach for grid number E, and for grid number E, all the columns are of size 500 mm by 500 mm. So we go to our model, do the same thing with this grid, go to left, select beams parallel to y-axis and define a new column of 350 by 350 mm. Left click on add here and then assign the member. And this is a square column, so we don't need to worry about the orientation. Similarly, we do select this whole grid here also, and on this grid delete the step column here, and on this grid what we do need to see is that all the columns are of again 350 by 350 mm. So select beams parallel to y-axis and selecting 350 by 350 mm size. So now we are done with the columns, and then last along these columns, all these columns are of size 350 by 600 mm except this column here. So we can select this column manually and assign 350 by 350 mm column size, and going to select. What we can do as a one more step is that we can go to select beams parallel to y-axis and unselect this particular column here and select 350 by 600 mm here. So if we check the orientation, now the orientation is correct. So now we have assigned all the column sizes, and after that if we want to define the beam sizes also, but before that what we can do is that we can go to support, create and fix support here. So we select all the joints here, and then we can just assign the fix support here. And after that what we need to do is that we also need to define the beam sizes, but before that we do need to define the sizes also for those beams. So going back to the plan here, so now we have a beam of span 7 meters. So for 7 meter and for like large amount of loading, the comfortable size shall be 350 by 600 mm. So we can select 350 by 600 mm here, and we can select all the beams here which are of maximum span. After that, for small beams, what we can select is that we can select 300 by 500 mm size, or we can also select 230 by 500 mm size, that is 9 inches. So selecting all the beams here, or what we can do to save our time is that we can go to select this beams here and go to select beams parallel to X, select beams parallel to Z, go to view selected objects only, and then select this beam here and go to select by inverse and inverse beam selection. So all these beams we can assign the size of 230 by 500 mm. Or to keep the beam bottom level as same, we can assign 600 mm depth only. This is cause otherwise there will be 100 mm tuck on the intersections. So to avoid that, we can follow this approach. And if we go to select by missing attributes, by missing property, here we can see that all the beams have been assigned the properties, and now we have also assigned the supports here. And after that, if we want to go to the specifications here, so we do need to make sure that all the beams have been assigned this particular specification. So now we have assigned the specification also. And if we see the specification for a particular flow, so here all the beams are resting on the columns itself, so there is no need of providing any release except on this particular junction. So after that, what we do need to do here is that we also need to be aware of what are the cracking coefficients. So we always design the structure for the cracked sections, so we do need to apply the property detection factors also. And so as per the IS 1893-2016, for structural analysis, the moment of inertia shall be taken as in reinforced concrete and masonry structure 70% of I gross for columns and 35% of I gross for beams. So this is the clause that takes care of the cracking coefficients. This approach is followed by the American code also. This approach is followed by the European code and Canadian codes also, because this is the fundamental behavior or the property of a structural reinforced concrete section, that it shall get cracked, and after cracking the moment of inertia shall get reduced. So how we can apply that in our model is that we do need to apply 0.7 for columns and for 0.35 for beams. Some people are of favor that we should apply torsional constant of 0.001, but I don't favor that approach, because it is if you are doing that, then it's well and fine, but you should also do the detailing of torsional constant of 0.001, and providing torsional constant of 0.001 and its appropriate detailing is not that simple. So that is why if torsion is coming on a beam, then it should be our tendency to design the beam for that particular torsion instead of running away from that particular problem. So left click on add here, and we go to select beams parallel to X, select beams parallel to Z. So now we have selected all the beams here, and then we are assigning 35% of moment of inertia. And after that, we again go to beams parallel to Y and assign 0.7 of IG for beams. And if we are doing the dynamic analysis of this particular structure, I'm repeating, when we are doing the dynamic analysis, so in this school structure, as most of the people here who are attending this lecture are already familiar with the static analysis, so in this lecture I am taking the dynamic analysis, because that is a more refined approach or a more modern approach to do the analysis and design. So coming back to our point here, so what we need to do is that we do need to assign fixed diaphragms, and how we can assign fixed diaphragms is that we do need to take care of the levels here, that is 3.5, 7, 10.5 and 13.7. so we go to node, floor diaphragms, height 3.5 meters, left click on add, and master node information is like you should left it to calculate only, because the software will make a pseudo node for this particular approach. So left click on add, and then again left click on height, select as 7, 10.5 and 13.7. This was the level plus 3.5. so we need to select all the nodes that are at level plus 3.5, and then we need to assign to selected nodes in yes. Similarly for height of 7 meters, this is basically height of y 7 meters, so we need to select all the nodes here and then assign and yes. Similarly for 10.5 meter level, and similarly for height plus 13.7 meter level. So now we have assigned all the diaphragms properties here. So in this lecture, first of all, we shall start with understanding what are the parameters to calculate the wind load as per the Indian standards. So first of all, we should understand what are the different clauses that are given to calculate the wind speed, to calculate the wind pressure, to calculate the wind pressure coefficients, and what and how we can assign that particular wind load to a particular structure. So the basis of calculating wind load on the building is given as per this clause. So what we need to have as an input is what is the VB, that is basic wind speed, K1, K3, K4 and K2. K1 is the probability factor, K2 is the terrain roughness and height factor, K3 is the topography factor, and K4 is the importance factor for the cyclonic region. And here we can calculate the value of, first of all, after calculating these coefficients, we need to calculate the VZ, that is design wind speed. And after calculating design wind speed, we do need to calculate a design wind pressure. So wind pressure is PZ, that is equal to 0.6 into VZ square, that is whatever value we have calculated here. And after calculating PZ, we shall again calculate a design wind pressure PD. So PD is the thing that we shall be applying on our structural model. So PD shall be KD into K into KC into PZ. KD is the directionality factor, KA is the area averaging factor, and KC is the combination factor. And all the relevant sections have been given here. So you do need to have IS875 part 3 in your hand when you are listening to this lecture. So this is the graph that is given, and this is the plan, and this is the elevation. So when the wind is being considered along this direction, this is A and this is B, and this is the wind force F that shall be calculated, and this is the elevation. So as we can see here that this is the height H and this is A here. So if H upon B value is greater than 1, then we do need to refer this graph. Otherwise, if H upon B is less than 1, then we do need to refer to this graph here. So coming back to our structure model, we can consider this is basically the graph that is given in the IS875 part 3 or NBC 2016. So if we are considering, let us say our structure is in Varanasi here. So if our structure is in Varanasi, then the basic wind speed shall be 47 meter per second. So we can enter VB here as 47 meter per second. K1 probability factor. Probability factor for this type of structure shall be 1 only, and that is thoroughly explained in this section 6.3.1. And K3 and K4 values. K3 is topography factor. Considering the building is on the plain level, K3 value shall be taken as 1, and K4 importance factor for the cyclonic region. So if the structure that we are constructing is in the range of 60 meters from the sea, then we do need to take the K4 as 1.2 as a cyclonic region factor. But considering Varanasi is not near to the sea, then we can take K4 value as 1. K2 is the like terrain height multiplier factor, so it do varies as per the different heights here. So coming back here, we have calculated these 4 values. After that, KD, KA and KC. KD and KC for this type of structure is 0.9. You can read these clauses in IS875 part 3. Then there you can easily understand how we have calculated or how we have taken the 0.9 here. And for frame windowed calculation, it is 0.8, and for cladding it shall be taken as 1. So terrain category factor we can take it as 3. And now we need to enter the building direction along and building dimension across wind direction. So considering this structure here, so if we are talking about this particular dimension here, then this is 13.8. From this point to this point it is 58, and from this point to this point it is 13.7 again, and then on this dimension is also 58. So we can consider this dimension as 58 and this dimension as 13.8. So coming back to our Excel file, now this is when we are considering wind load along this direction, that is wind WLX. Then on WLX we can take B value as this 13.8. So we can enter 13.8 here and A value as 58. So A upon B value is 4.2 and H upon B value is 1.8. As H upon B value is greater than 1, then we shall refer to this graph only. So A upon B value is in the range of 4.2. It is lying outside this range here. And H upon B value is like 1.8. So we do need to refer around here. So we can see that CF value is near to the range of 1 only. So we can take CF value as 1 here, and after that, now we have calculated the CF value also. Now we have calculated the KD, KA and KC and these A upon B values and H upon B values. Building dimension above the ground level. Yeah, this is the value that is incorrect in our model. This is in the range of 15.8. So we do need to enter 15.8 here. So now our H upon B value is 1.1 and A upon B value is again 4.2. So CF value is again 1. So when we are considering wind load along X direction, then we can enter the values here. So story height in our case is 3.5, 3.5, 3.5 and 3.2. And K2 values are for 3.5 meters. For terrain category 3, it is 0.91, for 7 meter also again it is 0.91. For 10.5 we can take it again 0.92, and for 13.7 we can take it as 0.95. So VB into K1 into K3 into K4 is 47. When we are multiplying this with K2, the VZ is coming out with this. PZ is nothing but 0.6 into VZ square. It is coming like this. KD into KA into KC, it needs to be minimum 0.7. And when we multiply these three numbers, we are getting 0.9 into 0.8 into 0.9. We are getting less than 0.7. So that is why we have taken KD into KA into KC is 0.7. So PD is nothing but 0.77 to 0.84 for 13.7 meters. So we do need to add a wind type definition here. So we can enter comments as WLX. That is when we are considering wind load along WLX. We can just copy paste this data here in our Excel file, and height we can enter it as like this. So now we have defined the wind intensities and height, and then left click on add. We can add factor as 1. Exposure factor is also by default 1, so we don't need to worry about this exposure factor. And after that we do need to again define the wind definition along WLZ. So in this part we just need to swap these values here. So instead of 58 it shall be 13.8 and this shall be 58 here. So now we can see that h upon v value is less than 1, that is in the range of 0.3. So h upon v value for 0.25 and 0.5, it is in the range of here, and a upon b value is 0.2. So we can see that CF value is 1.2 here. So we don't need to multiply the CF factor here, but when we are defining the wind definitions here, then in that case we shall multiply that with 1.2. So keep this point in your mind. I shall enter this data in the next lecture, but before that, here we can see that the we should enter the same values for this wind load along z direction also. So as our CF value is 1.2, then what we can do for here is that we can multiply the PD value with CF value. So here we can enter the formula of this into this. So copy paste these values here, and then add the wind intensities here, and enter the heights here. Left click on add here, enter the factor as 1, and left click on assign to view. So now we have defined the two types of wind definitions for our structure. After that we do need to access the seismic definitions also. So when we left click on add here, we need to select type as IS13920 here, as we need to check that what is the zone factor for Varanasi. So going to the page 490 of NBC 2016, here we can see that Varanasi is lying in the yellow color, and yellow color is nothing but zone 3. So considering zone 3, we can also left click on generate here. We can check that whether Varanasi is available here or not. So here we can enter Varanasi. So for Varanasi, Z factor is 0.16. We are defining, we are going with ductile detailing only. So we can select special RCC moment resisting frame SMRFS5. This is an important building as per the IS1893 2016. So I value shall be 1.5. We can consider resting it onto the medium soil. Damping ratio is 5%. Structure type is RCC frame building. Left click on generate here. We also need to calculate the period along the X and Z direction. As this is a frame with the brick filling, so we can calculate the time period with the help of formula 0.09 into h upon root t. That formula I will explain you right now. So this is the IS1893 2016 pages where it is showing that how to calculate the time periods for different types of structures. So the approximate fundamental translation natural period of oscillation. For bare moment resisting frames, it is 0.085 s to the power 3.5 by 4 for steel moment resisting frame building. For RCC, it is 0.075 into h to the power 3 by 4. And for composite, it is 0.08 into h to the power 3 by 4. Our building is for like here. So it is also guiding us with for building with RCC structural walls, and for other buildings like in our structure. So the formula is 0.09 into h upon root d. So the d is the base dimension of the building along the consideration of earthquake shaking. So in left click on add here and close. So in this case, when we are considering earthquake along x direction, the d is 58, and when we are considering earthquake along z direction, the d is 13.8. So coming back to our Excel file, we can enter a simple formula. So it is in our case the zone factor is 0.16. This is Varanasi. This is just an Excel file for your record. It's not like it will automatically calculate the values. I'm just like guiding you how we can make a standard for your easy calculations. The height is 15.8 and the dimension along X is 58 and along Z is 13.8. So time period along X is 0.09 into height of the building divided by square root of this value. So the time period is this divided by this into 0.09. So this is 0.09 into h divided by square root of d. So the time period along x is 0.187 and similarly time period along z is, so along x it is 0.187 and along z it is 0.383. So we do need to enter 0.187 here and 0.383 here. And I shall request you to read the IS 1893-2016 very carefully. If you are designing structures as per the Indian standards in the earthquake prone regions, then you shall have a thorough understanding of what are the different clauses of IS 1893-2016 and how you need to apply that in your structure. So this was just a seismic definition and wind definition. So in the next lecture we shall learn how to define the different load cases and how to define the different load combinations as per the Indian standards. So in the previous lectures we have already learned that how we can define the wind definitions and how we can define the seismic definitions. Now we move on to the load cases details. So after defining the wind and seismic definitions, we need to define the load cases details. So left click on load cases details here and left click on add option here. Now you will find a add new load cases window on which you will find primary, load generation, defined combination and auto load combinations. So in the primary you need to select the number. Loading type, first of all we need to start with seismic only. So if you are doing the seismic analysis of a structure, then first of all you need to enter the seismic load cases, and then after that you need to select the dead load, live load or wind load etc. cases. So first of all we have already entered a load case detail named as ELX. After that we name it as ELZ, that is the earthquake load cases along both the horizontal directions. And after that we can select ELY, that is vertical earthquake seismic force here. After that we can select dead load here, that is DL. We need to select now live load here. After that we need to define the wind load cases. So we can define WLX, that is wind load along positive X, wind load along minus X, wind load along Z and wind load along minus Z. And after that if we want to do the response vector analysis, we can enter RSX, RSY and RSZ. So now we have defined first of all the three seismic load cases along X, Y and Z direction. Then after that we have defined the dead load, live load, wind load along both horizontal directions and response vector along X, Y and Z. So if we are not doing the response vector analysis, then we don't need to define these three load cases here. And if we are doing only the static analysis, then only we need to define these three load cases. And you must know here that in STAAD, if we are doing the static earthquake analysis, then we do need to define the seismic forces before we define the dead load and live load cases. And after that, there is one more point that you should understand here, that usually people have this perception that they only define this X and Z, that is earthquake along horizontal directions only. But for the high seismic areas and for large cantilevers, and for when you're doing the analysis as per the American standards, then you do need to define the vertical earthquake cases also. As per the IS 1893-2016 or Indian standard for earthquake, you don't need to define the vertical earthquake for the low seismic zones. But I am defining here just to have you a syntax, or just to give you an idea. This is my workflow here. So whenever I design a structure, I always keep these load cases here. And for example, if I don't want to define the response spectre analysis, or if I don't want to define the wind load cases, then I can leave the options here empty. So we will move on to this particular point in the later lectures, but now I hope you're clear that how you can define the different load cases. After that, first of all, you need to define the dead load here. So dead load self weight has to be entered as -1. So those users who are comfortable with ETABS and SAP to the software, they enter this value as +1. But if you're doing STAAD, then you do need to enter this value as -1. And left click here, and then left click on assign to view here. After that, you can define the live load cases also, and the wind load cases also. But as we have already defined the seismic definition here, so we can left click here, left click on add here, and then left click on seismic loads here. So we can select the direction X and factor as +1. And similarly, we can select the Z, that is seismic load, Z and 1. Now as our building is in low seismic zone, then we don't need to define this ELY. And if we see the earthquake code for India as per the Indian standards, then you will see that for mutually orthogonal directions, for the building which has its axis along mutually orthogonal horizontal directions, there are these particular load combinations defined here. And for vertical earthquake effects, we do need to take the vertical earthquake effects only when the structure is located in seismic zone 4 or 5, structure has vertical or plan irregularities, structure is extended on soft soil, for bridges, for long spans, or for structure has large horizontal overhangs of structural members or subsystems. So if a structure has any one of these 6 particular points, then you do need to define the vertical earthquake, that is ELY also. But as our structure does not have any of these particular points, so we can skip the ELY here. And after that, we have already defined the self weight, and that is dead load along both the axes. And similarly, we can define the wind load cases also. So we left click on wind load here. Now there are various options that are available here. So in the previous lectures, we have already studied much about how we can apply the wind loads cases for all the structures. So in this structure, we do need to define the wind load for Y0 to Y13.7. So we can select Y14 here, and we do need to select the this wind definitions along X direction only, and X range we can define as -0.1 to +0.1, and Z we can define as from 0 to 13.8. Let us say we enter the value as 14 here. So left click on add here. So now we can see that we have defined the wind load along WL X direction. So if we see the wind definition here, so for type 1 when WL X is defined, and for type 2 WL Z is defined. So similarly, we do need to define the wind load along -X direction. So we select the factor as -1 here, and we do need to select X from 57 to 59. So we can take it here as 57.8 to 58.2. This is just to define a range, as our X coordinate is 58, so that is why we are defining this range. And Y is from 0 to 13.7, so we can enter 14 here also. And Z ranges from minus 2.2 to 11.5, so we can enter minus 3 to 12. So left click on add here. So now we have defined the wind load along minus X direction also. Similarly, we do need to define the wind load along plus Z direction. So from X equal to 0 to X equal to 58. Now we need to select the type 2 here. So from X equal to 0 to 58, Y equal to 0 to 14, and Z we do need to select here as from minus 0.1 to plus 0.1. So left click on add here. So we do need to select the Z direction here. So we can close this window here, and after that we do need to define the WL minus Z also. So wind load, and when we see the the building in the plan view, then we do need to define the three ranges here. So from X equal to 13 to X equal to 54. So from 13 to 54, and we need to select the Z windward phase here. We can select the factor as -1, and Y equal to 0 to 14, and for Z we do need to select 9.4 to 9.6. So left click on add here. So now we have defined the wind load along this phase. Similarly, we do need to define the wind load for this particular these 4 frames here. So we do need to select another property here. So we left click on wind load, Z, direction is -1. So from X equal to 0 to 13, and Y equal to 0 to 14, and for Z we do need to select 13.7 to 13.9. So left click on add here. So now we have defined wind load for this phase also. Similarly, we do need to define the wind load for this particular small 2 frames. So from X equal to 54 to 58, Y equal to from 0 to 14, and for Z we do need to select here 11.4 to 11.6. So left click on add here. So after defining wind load for X, minus X, Z, and minus Z. So now we are finished with defining the wind loads, and after that we do need to do one more thing here. When we are defining these ELX and ELZ parameters, we do need to go to the editor file here, and we do need to enter the perform analysis and change here. So if you are if you have some experience with the STAAD software, then if you don't enter this data here, then it will show an error that if this UBC analysis has tension or compression. So to avoid that error, you do need to enter this perform analysis and change command here. So you do need to take care of this particular syntax here to avoid that particular warning. And now after that we do need to define the slab loading and brick wall loading. So we will do that in the next lecture. So in the previous lecture we have learned how we can define the static earthquake load cases, how we can define the wind load along all the 4 directions, and how we can define the self weight. So now in this lecture we shall learn how we can define the dead loads and how we can define the live loads. See, dead loads are nothing but just a simple math that we need to calculate the density of material, and then we need to multiply that by the thickness of that, and then we can apply the equivalent UDL on that. Live load is something that is guided by the codes. So for example, if you are referring the loading for the American standard, you need to refer the ASCE 07. If you are referring to the Indian standard, then you need to refer IS875 part number 2 for the live loads and part 1 for the dead load calculations. So dead load is nothing but just a simple math, and then we can take a simple example here. So for example, if we want to, this was our first floor plan. So on this first floor plan, we have some brick walls over here, and we have some partition walls over here. So for example, considering all the brickworks are of 9 inches thick, that is 230 mm thick, then how we can calculate the loading of the brick wall on the beam? So what we need to do here is that, let us say the height, we first of all need the height of the brick wall. Now if we refer to our sections here, the floor height is in the range of 3.5 meter. So considering the height of the beam is 450 mm, so what we can say here is that the height of the brick wall is 3.05 meter. After that, the density of the thickness of the brickwork. Thickness of the brickwork is nothing but 9 inches, so we can refer here to 0.23 meters. After that, density of the brickwork, it is 19.2 kg per meter cube, 19.2 kilonewton per meter cube. So if we want to calculate the UDL, so we need to multiply all the terms here, that is 3.05 into 0.23 into 19.2, so it is 13.47 kilonewton per meter here. After that, we need to calculate the thickness of the finishing also, that is the thickness of the mortar on the brickwork. So let us say we are applying 12 mm plaster on both the side, so it comes out to be 0.024 meter. Density of the mortar, it is in the range of 24 kilonewton per meter cube. So height of the mortar is same as the brickwork. So the UDL is coming out in the range of 0.024 into 24 into 3.05. So the weight of the mortar is approximately 1.76 kilonewton per meter. So total UDL is nothing but 1.76 plus 13.47. So 15.3 we can take that on the conservative side. So 15.3 kilonewton per meter is the UDL. So going back to our model here, so in this model, here we can see that on the grade slab we shall not apply loading of the slab, so we shall only apply the loading of the brick wall here. So all the external partitions except for this one, the brick wall is coming, or except for this one. So we start from this grid here. So on this grid, from this point to this point, the brick wall load is coming. So we go to dead load here, left click on member load here, uniform force, here we can enter this particular value, that is 15.3. So minus 15.3 kilonewton per meter. Let's select the global direction as GY, left click on add here. So we can select all the beams here. Left click on assign to selected beams and yes. So now we have applied the loading of the brickwork here, and after that the profile is rotating like this. So we do need to apply the brickwork loading here and then along all along from this point to this point. You should notice that like we are applying a door here, so we can take the brick wall on the conservative side. But if like I have seen some engineers who are very typical about all these things, so what they do is that they apply a brick wall loading from this point to this point and from this point to this point, but in the meantime like they don't apply the loading of the door here. So although door is a light material, so but if you are like doing that much amount of calculation, then you do need to do this small calculations also. So this is just like my recommendation. My recommendation is always like always go for the conservative side. So there is no harm in like going for that. So selecting this beam here, then this, and then this. So now we can select the beams here, and after that from this point to this point and all along this point. So although there cannot be a brick wall here, so what we can do here is that we can apply loading from this point to this point. So taking the beam here and then here. After that we do need to apply dead load for a particular length here. So the beam starting point is from left. So what we can do is that we can go to member load, uniform force, this -15.3, and then we can select that from D1 0, the D2 is only from this point to this point, so approximately 2 meters here. So we can enter D2 as 2 meters here. So let us see that whether this nomenclature is correct or not. What we can do is that we can go to tools, redefine incidence, and switch incidence of selected beams. So here we can see that now the loading is correct. So after that 1 2 3 4 1 2 3 4 5 6 and 7. So 1 2 3 4 5 6 and 7. And after that here we can see that only there is an opening here, and then after that we do need to apply 1 2 3 4 5. 1 2 3 4 and 5. Similarly there is an opening here, and we do need to apply the brick wall loading on these two beams also. So after that we move on to the interior beams. So all along from this point to this point we have this brick wall loading. So what we can do in this case is that we can select all the beams here. So now we applied the brick wall loading on the interior beams also, and then after that 1 2 and 3. So 1, 2 and 3. While selecting beams, make sure that no column is selected. So cause some people, what they do is that while selecting the beams in the plan, they also select this column, and accidentally they apply the loading on this column also. That is a wrong practice to do. So always take care of what you are selecting, and after selecting, it is recommended that you should also check that in the isometric view. So every alternate beam is now loaded. So 1, 2 and 3 and 4. So 1, 2, 3 and 4. After that, again you can see that this brick wall is also existing here, and then this brick wall is also existing here. So what we need to do is that we need to model a beam for this particular brick wall also. So the approximately distance is in the range of 0.475. So we can model a beam at an offset of 500 mm here. So we select this node here and select Z as 0.5 meter. And go to geometry, add beam by perpendicular projection. So now this beam needs to be released on both the ends here. And while applying the loads, you need to have a 1 brick thick wall loading here. And similarly, when we are checking this arrangement here, so now we do need to apply brick wall loading on this particular beam also. So now we can check that we have now applied all the brick wall loadings except for this particular frame here. So 1, 2, 3. And 4. After that, we need a beam for this particular wall also. So we can go to geometry, add beam between midpoints option. So we can apply a loading on this particular beam also. So now we can check that we have applied loadings on for all the brick walls here. And as discussed earlier also, we don't need to apply a slab loading on this particular floor, as this is resting on the ground. So after that, we move on to the next floor here. So all these particular floors are typical here. Here we can see that we have not did a mistake here. As I was discussing with you earlier also, that if we accidentally select the columns also, then the loading looks like this. So we can left click on toggle load and left click on assign to selected beams. So with this we can toggle the 15.3 kN per meter vertical loading on this particular column here. And after that, as discussed earlier also, that the loadings on all these floors are typical. So we can select all the floors simultaneously, and then we can apply the loadings on all the 3 floors by selecting all the 3 beams in a single plan view, thus saving time. So we select go to the second floor plan here. So here we can see that every alternate beam is loaded with full brick thick wall. So we can select all the beams here, and then this particular beam and this particular beam. So before that, let's check that height is same or not. So here we can see that height is same except for this particular floor. So on the top floor, we do need to apply the lesser loading, but conservatively, to explain you the concept, what I am doing here is that I am taking the loading on the conservative side only. So if you are designing that in the real life, so what you need to do here is that you need to take the lesser height here, and then accordingly calculate the load and then apply the loading on the top floor. So to save the time, what I am doing here is that I am applying as loading on all the floors, as considering the height of the brickwork as 3.05 meters. So checking that in the 3D view, so now we can see that all the beams are selected here, and after that we do need to go consider the profile like this. So as a common sense, we can see that all the perimeter beams are now covered here. So what we can do like here is that select all the periphery beams, and apply a loading of 15.3 kilonewton per meter here. So now we can see that we have now applied the loading of 15.3 kilonewton per meter on all the peripheral beams. And after that, we do need to see here whether there are some extra walls here also. So for that, what we need to do here is that we do need to select all the beams from this point to this point and apply a loading. And after that, these two beams here, and 1, 2, and we do need to apply loading on these two beams also. After that, 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, and 6. In real life, what I do is that I take a printout of all the architectural drawings, so that I don't need to switch to and fro between the CAD drawing and the STAAD model. So that practice also helps us in saving me lots and lots of time, because I don't need to switch windows when I'm having a printout in front of me. And now we have applied the brick wall loading for all the floors. And for parapet, what we can do is that we can just calculate the loading for the parapet on the top with 0.9 meter height. So what we can do here is that we can just copy paste this particular calculation here. Instead of 3.05, we can select 0.9. So the parapet loading is coming out to be in the range of 4.5 kilonewton per meter. So we name a dead load case here, and for member load we can enter minus 4.5. So now we have assigned the parapet loading on the top as minus 4.5 kilonewton per meter. So with this approach, now we have calculated all the dead loads except for the staircase loadings. So here we can see that staircase dead loading needs to be considered here, and the dead load due to slab also needs to be considered here. So considering the spans are very short, in the range of 3.5 to 4.5 meters only, so we can take 150 mm slab comfortably for this type of arrangement here. And the slab is also two-way here. So here also we can see that this span is also two-way span. So what we need to do in this case is that we do need to define the groups also. So what we can do is that we can select all these floors here, for which we do need to define a group here. As all these floors are typical, so that is why I'm defining the group in a single go. So we refer to the architectural drawing here. So here we can see that for for corridor the live loading is different, for classroom the live loading is different, and for these washrooms area that we are seeing here, the loading is again different. So in the next lecture we will learn how we can calculate the dead load due to slab, and how we can calculate the live load for different type of rooms and different types of arrangements. So in the previous lecture, we have learned that how we can calculate the brick wall loading and how we can assign the brick wall loading to the structure. Now in this lecture, we shall learn how we can calculate the dead load due to the slab and how we can assign that with the help of groups option. So now there are two concepts with which we can apply the floor loading in the STAAD software. Number one approach is that most of the people do is that they go to this add option here, then they go to this flow load option, and then with the help of calculating by all these coordinates, they put on the values here, and then enter the value, and then left click on add and close here. So that approach is very lengthy approach, and it tends to waste a lot of time on the part of a structural engineer. So what my shortcut is that what I always do is that I select the floor here, and what we can do is that now press Ctrl+G option on my keyboard, and we can name it as second floor, or we can enter second classroom loading. So it means that the floor is second, and the the type of the slab on which we are applying loading is 2 and classroom. Selecting type as floor, and left click on OK here, and then this create group window will option. Create group window will open, and here we can see that the classrooms that we have in our structure is 1, 2, 3, 4, 5 and 6. So we can select these 6 slabs here or beams here, and let us cross check the dimensions. From this point to this point, it is approximately 54 meters. So here we can see that 54 meter is the length of the length for which we need to apply the classroom loadings. So we'll left click on associate here, and then after that these are the slabs on which we are applying the ramp loading. So ramp loading needs to be applied on all of this floor here. So what we can do here is that we can name a group here, and then we can enter 2 and ramp. Select type as floor, and then left click on OK. Select the beams here, and then left click on associate. So the advantage of this by making groups is that we can specifically apply the different live loadings or different dead loadings for the different type of occupancies. So what may happen is that, for example, let us say in this classroom structure, as the span of the slab is very high, sometimes it may happen that you do need to take the thickness large thickness, or higher thickness here, and then lower thickness, let us say in the case of this corridor. Or what we usually encounter is that in the washroom area, what usually happens is that due to the sunken portion or due to the superimposed finishing loads that comes on in the washroom area, we may need to apply a higher value of live loading or a higher value of dead loads. So to account for all of these problems, so my approach is usually that I name the groups and then apply the loadings. So these are the corridor areas. So left click on create here, and to corridor. Select type as floor, left click on OK, left click on associate, and this is the washroom area. So left click on 2 and select type as floor, and we can enter this as left click on associate. So this is nothing but the washroom area loading, and this is the panel for the staircase. So what we can do here is that we can model the mid landing beams, and then we can assign the UDL. So that we will do in the separate lecture, but in this lecture you should be clear of how these groups behave. So what we can do here is that left click on close here, and then left click on dead load. Let us say the thickness of this slab here we want approximately in the range of 150 mm. So for 150 mm, what we can do is that we can say that the thickness of slab is 150 mm. The density of concrete is RCC, let us say it's 25 kilonewton per meter cube. So multiplying thickness with density, we can get the flow load. So it's nothing but 150 into 25 divided by 1000. So it is 3.75 kilonewton per meter square. After that, we can say that, let us say the finishing thickness is 50 mm, and density of the finishing material, let us say it is simple PCC, we can enter it as, let us say 24 kilonewton per meter cube. So the flow load for finishing is in the range of 50 into 24 divided by 1000. We are divided by 1000 as the unit is in mm here, and this the unit is in meters here. So the total flow load is 3.75 plus 1.2, so 4.95 kilonewton per meter square, or we can apply 5 kilonewton per meter square. Similarly, in the case of the washrooms area, let us say the finishing is in the range of 150 mm. So the total weight is coming in the range of 7.35 kilonewton per meter cube. And after that, let us say the terrace loading, or like the terrace slab, it also contains the waterproofing. So let us say the waterproofing thickness is in the range of 250 mm. So let us say the density of the waterproofing is in the range of 22. So the weight is coming out in the range of 9.25 kilonewton per meter square. So there are three values here for different floors. For a general floor, we need to enter 4.95 and 7.35. So we go to dead load here, left click on add flow load, and then we can left click on group. So here we can see that all the groups are now coming here. So we can enter pressure as -5 kilonewton per meter square and left click on add here. So now we can see that the STAAD has generated the flow loading for this particular area. And after that, we can do the same for the ramp area as well as for the corridor area. So we go to the group. Ramp we need to enter again as -5. Corridor also again we need to enter as -5. And for the washroom area, we need to enter the value as 7.35. So we enter the value as -7.35 here. So now we can see that for different loadings, for example, let us say if we select this loading, this is blue. So this is the corridor, this is the washroom area, this is the corridor area, and this is the ramp area, and this is the classroom area. So this is basically the easy classification for what we can adopt in our structure. After that, what we can do here is that now we have two options. Option I am giving to you because we do need to either repeat the same for the upper floors also, or what we can do is that we can change the definition of the group also. So what we can do in this case is that, let us say we select these 3 floors here. So in this case, what we can do is that we can left click on to classroom, and we can select all the beams here. So now we can see that in isometric, all the 3 floors are selected. So why we are doing this is because the geometry is same on all the floors. That is on the 2nd floor plan also, on the 3rd floor plan also, and on the 4th floor plan also, except for the terrace obviously. So in this case, what we are doing is that we are just changing the definition of this group, and left click on associate to selected geometry. After that we select all the ramp beams here and left click on associate. After that we select all the corridor section here, left click on associate. Make sure that you are selecting the correct beams, and how we can check, we can go to isometric view here and then we can cross check. And after that, this is basically the washroom area. So coming back to our model, so let us check that whether this loading has changed or not. So here we can see that the loading has not changed here. So these type of things do happen. So what we can do is that we can just go to editor file here, just change the editor file and reopen the model, and then we can check whether the thing has changed or not. So these graphical changes, it might do happen that you do need to regenerate the model in the STAAD also. So here we can see the typical floors are having the typical loadings. So this is basically the ramp loading, this is basically the corridor loading, and this is the loading for the washroom area. And after that, as discussed, the loading for the terrace shall be different. So we can select the whole terrace here, left click on Ctrl G here, and then left click create terrace loading, select type as flow, and select all the beams here. So we can go to dead load here, and then we can enter the value as 9.25 here. So we select the floor loads group and terrace minus 9.25 here. So here we can see that now the terrace live loading is also applied. So here we can see that how much time you can save by going to the group option here. So this is the the best option that you can use to save your time. After that, as now we have defined all the dead loads except for the staircase, that we will deal in a separate lecture. But now coming to the live load option here, so the live load we shall learn in the next lecture. So in the previous lecture we have learned how we can calculate the dead loadings. So now in this lecture I shall focus on how we can calculate and how we can assign the live loadings. See, for each country, let us say it is Europe or US or UK or this India, for each and every country has adopted a particular loading code, and in that code it is clear that how much loading we do need to apply for what kind of structure. So if you are referring to American standards, you need to refer ASC 07. The latest version was released in 2016. If you are referring to the Euro standards, you need to refer this EC0 or EC1. And if you are referring to this Indian standards, either you need to refer the IS875 part 2 for the live loading, or you need to refer this NBC 2016. So here I have opened the NBC 2016 copy. So here we can see that for on the page number this for part 6 structural design, section 1 loads, forces and effects, there is this clause for the educational buildings. So for in educational buildings, for classrooms and lecture rooms, the loading is 3 kilonewton per meter square. So here we can see that UDL is given here and concentrated load is given here. You don't need to be confused with this concentrated load kilonewton. Actually, basically the code is guiding us that we do need to refer to the point which gives us the most severe effect or the maximum bending moment or shear force values. So as a general practice, we do refer to this UDL value, that is kilonewton per meter square value only. So for classroom, the loading is 3 kilonewton per meter square. For the corridors area, it is 4 kilonewton per meter square, and for the washrooms area, that is toilets and bathroom, it is 2 kilonewton per meter square. In addition to that, if your building has this restaurant area, the loading is again 3 kilonewton per meter square. And if you have some offices, lounges or staff room, it is 2.5 kN per meter square. For dormitories it is different. For projection room, obviously the student concentration may increase, so that is why they have taken the higher live loading, that is 5 kN per meter square. For storerooms, obviously the loading is high. And for libraries, this is somewhat interesting approach, that up to 2.2 meters the loading is fixed, and 2 kN per meter square shall be added for every meter beyond 2.2 meter. So let us say if the height of the library is in the range of 4.2 meters. So for 2.2 we need to refer 6, and then we do need to add 2 kN per meter square 2 times. So that makes us 1 ton per meter square loading. So these are the just basics of how you can access the live loading. Similarly, they have divided this institutional buildings also, assembly buildings also, business and office buildings also. So as a for further studies, you can read the codes, and then you can get a clear idea of how our code guides us about the live loading. So coming back to our lecture here, for classrooms we do need to apply 3 kN per meter square loading. So that is now for this structure very easy, as we have defined the groups here. So we go to the flow load option here, and then group. For let's say we select the classroom here, and then we enter the value as minus 3 kN per meter square. That is this value. So left click on add here. After that, for ramp, the ramp again the staircase loading shall apply. So it shall be 4 kN per meter square. And for corridor again it is 4 kN per meter square. For washroom areas, for the washroom the loading is 2 kN per meter square. That is this value. So we enter the value as -2 here. And for terrace, the loading for accessible terrace, the loading is 1.5 kilonewton per meter square. So as this code guides us in separate clauses about the terrace live loading. So here we can see that the imposed loading in various type of roofs. So for roof where the access is provided, it is 1.5 kN per meter square. So we enter the value as -1.5 and left click on add here. So here we can see that now we have assigned the live loading for different room occupancies. So now in this lecture, up to this lecture, we have now defined the ELX loading also, ELZ loading also, dead load, live load, and wind load along all the directions. So in the next lecture, we shall deal that how we can calculate the staircase loading, and how we can apply that on our structure, and how we can plan the structure of the staircase as per our framings.